Okay, this is, I believe, 1.9, 1.10, 2.1, 2.18 course questions document. Uh, we don't have. Oh, the last periodic I did, yeah, it was up until 1.7. So, okay. You know what I'm gonna do now? I'm gonna do 1.8, but skip this. It's not required for the periodic. If you're watching for the periodic on October uh, 7, October 7, if you're watching for the periodic for October 7, skip what I'm about to do now, 1.8. Skip until I start question 30. I'm just gonna record this for finals, since when we have finals, I don't have to record again. Um, yeah. Anyway, why would fur coats keep their owners warm if they were worn inside out? Let me. Oh shit. Go to here. Is this mechanics? It's mechanics. Open mechanics. Hold up. Basically, if you wear the coat inside out, يعني outside, like opposite, trapped air forms very good insulator. So انت يعني it will cause air bubbles. And when you have air, it's a very good insulator that prevents heat from escaping, right? Why are woolen clothes worn in winter? Because the woolen clothes will cause air. They preserve the thin layer by reducing convection. Okay, they're just saying why. Why are fluffed up feathers more effective than no feathers? Okay, because when you have feathers, again, they preserve the thin layer in contact with the body by reducing convection. How do they preserve it? By creating an air layer. Why in a windy weather we always feel colder? Because convection, right? The air is blowing on you, which causes forced convection, right? Why is it forced? Because there's a force acting on you in the wind, right? Describe the transfer of heat by convection. Convection is made of heat transfer that takes place in fluid. In this method, heat transfer takes place with actual motion of matter from one place within the body to the other. When water is heated, the bottom of the container expands and becomes lighter since its density decreases. Very important that you know that the main cause of a convection of motion is because of the change in density. The warmer and less dense water moves upwards, forming the cold and denser water at the top to come down and thus get heated up and rising again. This forms convection currents. Okay, what many people make mistake is that they say it's due to temperature when it's actually due to the change in density. Okay, هلا 1.9, this is actually for the periodic. Draw a simple diagram to show the construction of a vacuum flask. Explain how the use of vacuum flasks reduces heat transfer by conduction, convection, and radiation. Very, very easy. To draw it, they obviously won't ask you to draw it in the periodic, but they might ask you to label it, right? This is the stopper here. This is the double-walled glass vessel. This is the case. Okay, this is the felt pad. These are the silvered surfaces, and this is the vacuum is trapped in between. How does it stop conduction and convection? It completely stops it, right? Because of there's vacuum. Vacuum completely stops it. What does it do to radiation? The silvered surfaces reflect back the radiation and prevent it from escaping the fast. Very, very easy. An electric filament lamp with a clear gas bulb is switched on and gives a bright white light. The bulb contains a small quantity of argon. Give an account of the parts played by conduction, convection, and radiation, the loss of heat from the lamp filament. Okay. Oh my god, what's all this? Okay, by conduction. The lamp filament gets hot when the bulb is switched on, right? Because the argon gas is in contact with both the gas and the filament, conduction will take place. Filament being emitted, okay, is good so heat. Okay, this is all yap. What's this stupid question? Okay, let's see. Argon gas, okay. Okay. Okay, I'll summarize this. By conduction. Okay, the lamp filament is that lamp or is the light bulb which has this thing in the middle, right? Okay, so what happens is the lamp filament gets hot, it conducts, right? The argon gas is in contact. The argon gas, it's in contact here. Okay, so why does it conduct? The heat will flow through the filament rod, okay, and it will flow to the argon gas, which will thus conduct to the glass on the outside of the filament lamp. Okay, uh, convection currents take place in a gas. For convection, as the gas gets hot, right? What's gonna happen? There's gonna be some convection. Whenever a gas gets hot, obviously there's gonna be convection. The hotter one goes up, with the colder argon goes down. That's it. Radiation. All hot bodies give off radiate energy. So the filament of the lamp will emit some radiation energy at the start, right? Which heats up the gas, which in turn heats the glass bulb, which in turn heats the air outside. Yeah, I tried to summarize. I don't like this question. Very stupid. I don't think it will come. Describe the transfer of heat by radiation. This is a good question. All grids you must know, okay? Radiation is defined as the flow of heat from one place to another by means of electromagnetic waves. So, let me ask you define. Radiation is the flow of heat from one place to another by means of electromagnetic waves. Okay, you should know that radiation has all the properties of electromagnetic waves and it can travel through vacuum. Okay, remember it's emitted in quanta, meaning it's quantized, emitted in discrete amounts of energy. What is the energy of photon having this amount of hertz? Use H equals this. You know, E equals HF. You just multiply them and you get this. Okay. Identify which colors are best emitters, absorbers, and reflectors of radiation. This came also. You should know that the black color is the best absorber, and since it absorbs the most, it should also release and emit the most. White color is obviously the best reflector. Give 3 different ways to keep the house warm during winter. This is nice. It is important. Double glazing, right? Loft insulation, floor carpeting, and so on and so forth. These so far they're very self-explanatory questions. Just memorize. In many hot countries, it is common for houses to produce hot water using solar panels. The figure shows a cross section of the solar panel. So here you have a copper pipe painted black. So this is like you're looking at it from, you're looking at it from the side. Okay, metal backing sheet, sunlight, la 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 la, trapped air, water. Okay, why are the pipes made of copper? Actually, the pipes will be made of copper because they're good conductors. So, when the heat from sunlight comes, we want it to hit the copper and conduct the heat to the water, right? Make it hot. Why are the pipes and metal backing painted black? Because the black color will absorb the most, right? Black color is a good absorber. We're trying to heat up the water. Remember, we're trying to produce hot water. An insulating material is attached to the metal backing sheet. So the heat doesn't escape, right? To reduce heat loss to the surrounding. Why did we insulate here? Why do we put insulator? So all the heat gets concentrated here and doesn't escape outside, right? Okay. Uh, the presence of the glass sheet increases the energy collected by the water. Where is the glass sheet? Here. Why? Increases the energy collected by water. Trapped air inside the glass. Huh? I think what they're saying, this glass sheet, it will come and reduce energy from leaving outside because it will come inside, okay, but it won't go outside because the glass has some air bubbles in between them, which prevents it from escaping outside. Okay, the heat. Very, very easy. These top questions, we won't do them because they're not required. Okay, even though he might say it in the material, but none of this is material for our periodic. Okay, so we're going to skip all the way down to here, page 11. We have a good, how many pages? 7 pages, right? 7 pages. Okay, not bad. Okay. Can a plastic rod be charged if rubbed against another plastic rod? No. Why no? Because for objects to be charged, they must be rubbed against different material. Okay, this was in the CA, by the way. They said, what would you rub glass against if you don't want a charge? You would say glass again, because you're rubbing it against the same material, which would not give you a charge. Now, to consider 4 charged objects A, B, C, and D, such that A repels B and it attracts C, and C repels D. If D is positive, what is the charge on B? Okay, this guys is so easy. Okay, A repels B, and A and B have the same charge. B attracts C, and B has the opposite charge to C, right? If you want to like draw this, put A, B, repel. Then you put B, C, attract. Okay, and then C repels D, and C و D repel. And C و D نفس charge. He said if D is positive, what's B? Okay, if D is positive and it repels C, and C is also positive. B and C attract, if C is positive, it's going to be opposite to positive. Okay, so what's B? Negative. Very, very easy. How many electric states exist? We know 2 exist, no, 3 exist: positive, negative, and neutral. Many people make the mistake of saying, oh, is new. Okay, 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 so it's just positive and negative, I guess. So don't say it's neutral. Yeah, I guess we all have something to learn. Okay, 5. Positive, negative, or neutral isn't an electric state. Okay. Determine how the charges would interact in the diagram below. Okay, أكيد here it's repel. أكيد here it's attract. أكيد here it's repel. Come on, guys. Okay, repel in A and C, attract in B. Okay. Give some examples of conductors and insulators. I'm just going to open the answer key. Conductors are usually metals and electrolytes. What are electrolytes? Substances that dissolve in water to produce conducting solutions. Like salt, it will produce Na plus C and minus. That's chemistry we're saying anyway. Insulators are usually non-metals like wood, plastic, etc. Right? Air is also a very good insulator. Differentiate between conductors and insulators. Conductors are materials that allow the flow of electric charge, but insulators limit that. Right? Okay. A metal rod is placed on a beaker. It's in contact with a light metal coated ball. You touch the end of the metal rod with a charged glass rod, and the ball at the other end is repelled. After the charged rod is removed, the metal rod still repels the ball. Suppose now that you touch the ball with a metal rod that you hold in your hand. What do you predict will happen and why? It should not be repelled anymore, right? The ball will lose its charge to your body. If you were barefoot, charges leak from the ball to your hand into the earth. You suddenly touch the ball with a metal rod and you hold it. Okay, it would lose its charge. عندك هون rod هون عندك ball, right? uh, okay, so it's repelling. Let me draw it a bit better, sorry. It's kind of repelling. It has this angle over here. It's repelling, right? You have this rod, and then you put another glass rod here. Oh, it's repelling. And انت you came and you touched it with your hand. When you touch it in your hand, it is gonna lose the charge. Will it repel anymore? No, it won't repel. Okay, so what's gonna happen? The ball will lose its charge to your body. If you are barefoot إذا ما كنت لابس من أجرك كنت حافي, charges leak from the ball through your hand and into the earth. Okay, I'm sure some of you who use electric stoves, um, they have experienced electrocution when they're barefoot because charges will leak through their body. It happens to the best of us. Define earthing. Earthing is when you bring it in contact with a much larger conductor, which may or may not be earth, right? Describe the process of charging by induction and earthing. Okay. To charge by induction means you don't touch it. Induction, there's two, right? Uh, they want this the second case. So okay. They don't want induction only. They want the one that has induction and earthing. The first thing is they get an uncharged metal sphere, and then they bring a positively charged or negatively charged glass rod near it, right? So remember this experiment. You have the ball, it's neutral, وعندك هون هلا positive sphere. قصدي positive rod. Okay, it's what's gonna happen. It's gonna attract the negative charges to the right, or the positive to the left, away from it, right? Then what did we say we do? We earth it. We momentarily earth. We touch it with our finger. When we touch it with our finger, what's gonna happen? It's gonna lose all these positive charges to the finger that you're using to touch, and it's only gonna be negative charges left over. Okay. So what happens? So without removing the glass rod, we earth it. So we touch it with our finger. After we earth it, we move the glass rod farther away, and now the metal sphere is left with a negative charge. Okay. Question 10. Okay, on. Suppose you hold a metal rod in your hand and you move one end of the rod towards a positively charged sphere running from insulating thread. What do you expect to observe? So you hold a metal rod in your hand and you move one end of the rod towards a positively charged sphere suspending from an insulated thread. Okay, what do you expect to observe? What will happen? Let me see. The metal rod will attract the sphere. Okay, apparently it's gonna attract because I think يعني شو هالسؤال سخيف. I think it's because the metal rod is neutral. We have a positively sphere. Neutral and positive will attract. There's an explanation. An induced negative charge will appear at the end of the rod closer to the ball, causing a net attractive force. Yeah, okay. Yeah, because look, عندك الرod, it's uncharged, but the ball positive. So this positive, what's gonna do is gonna induce the negative charges, right? And it's gonna take all the positive here. And what's gonna happen to now when you have negative all the way here and you have positive here? It's gonna cause an attraction force, right? Uh, you have two metal spheres of the same size mounted on insulating stands, a strip of plastic and a piece of paper. Uh, huh? What? You have two metal spheres of the same size mounted on insulating stands, a strip of plastic and a piece of paper. Describe what you would do to give the two spheres equal charges of the same sign, equal charges of opposite sign. Let's open the answer key. If you want the same sign, we rub the plastic strip with يعني what are they made of? Is one on plastic, one on paper يعني يعني you have to, I just understood the question. And you have two metal spheres and then you have plastic and paper. Okay? We rub the plastic strip with paper. You know, when you rub plastic with paper, you get positive paper and negative plastic, right? The strip becomes negative and the paper becomes positive. We touch one of the spheres with the paper, and then obviously that sphere will become positive. Because if you touch something with a positive object, then that thing is going to become positive. Then you touch the sphere, the positive sphere, to the second one, and the charge will spread to the sphere. Okay, yeah, okay, this makes very so much sense. This would work also the other way around. Let's say you rub the plastic strip with the paper, right? You take one of the spheres and you put it in contact with the positive paper. What's gonna happen to the sphere? It's also gonna become positive. Hala, the sphere is positive. If you put it in contact with another neutral sphere, مش صح, it takes the charge of the thing that's being touched by it. So since it's being touched by a positive object, it's also gonna become positive, right? So that way we have same charge, right? We have equal charge of the same sign. Okay. How about opposite sign? Opposite sign you can use induction. We rub the plastic strip with the paper, so the strip becomes negatively charged. Now, you're gonna put the two metal spheres on insulating stands so that they touch each other. The charge strip is brought near one of them, and the spheres are separated by pulling the strands apart. La 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 la. One is positive, one is negative. Okay, this one is the charging by induction. You have two spheres. Hey, remember this experiment? You'd bring the negative rod near it. When you bring the negative rod, why is it negative? Because we rub them together. We got this is the negative plastic rod. When you bring it near, this is all the positive charges will flow here. All the negative charges will flow here. What are we gonna do now? We're just gonna separate. We're gonna pull this one to the left. What's gonna happen? This is gonna be negative. This is gonna be positive. So now they have opposite signs. It's so easy, guys. Two metal rods. I hate these questions so much. Two metal rods are mounted on insulating blocks and aligned along a common axis with space between them. One is positive, the other is negative. A light sphere with a conducting coating suspended by a long insulating thread is introduced into the space between the rods. What do you predict will happen, and what reasoning do you base your prediction? Since charges have the same magnitude, nothing happens as the two rods tend to attract the sphere with opposite forces. True. Two metal rods are mounting. Okay. One, okay. 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 You have one positive. Okay. And you have one also negative over here. You have a bar in the middle. If it's at the same distance between them, this is gonna pull it with this force, this is gonna pull it with this force, right? So akid, they're gonna cancel out each other and the ball is just gonna stay still. But if you push the ball slightly, just a bit, maybe like a millimeter to the left, it's gonna be attracted to the positive sphere. Okay? Even if you pull it also a millimeter to the right. Okay, as long as it's the same distance, theoretically nothing's gonna happen. Two, okay, yeah. هلا 13. Two identically charged spheres are placed at a distance of 1 centimeter from each other. The magnitude of the force is 5. Modeling the spheres as point particles, what's the magnitude of charge on each sphere? It's identically charged. Okay, what's the equation? We know that F is equal to K Q1 Q2 over R squared. Okay, F, we know it's equal to 5 newtons. K, it's always 9 times 10 to the 9. Okay, it's Coulomb's constant. Q1 and Q2 are equal to each other. So you could just say Q1 equals Q2. So it's Q times, it's just the same as Q times Q, which is just Q squared over R squared. This has to be in meter, right? It's in centimeter. How do you change centimeter to meter? It's 1 times 10 to the negative 2. So 1 times 10 to the negative 2. And remember, we have to square it, right? Halla, you're gonna get Q squared. And then let's actually solve this. 5 equals 9 times 10 to the power of 9 times Q squared. Let's just call it X squared over 1 times 10 to the power of negative 2 squared. Shift sub. Okay, you're gonna get, you get this. What's that? 2.4 times 10 to the negative 7. Yeah. Okay, they rounded to SF. 2.4 times 10 to the negative 7. Okay, yeah. Okay, we only take the positive answer, no? This is the answer. Okay, this is their solution. They redistributed the equation. They took r squared there, divide by k, and by, yeah, you got, yeah, q squared equals this. So q equals radical force times r squared over k. And they got this. Okay, makes absolutely sense, absolute sense. Very, very easy. Uh, describe how bringing a neutral conductor close to a charged object causes attraction between them. Look, yeah. When you get okay, consider a negatively charged plastic rod and then a neutral sphere. When brought near each other, the positive charge within the conductor sphere are going to be attracted to the negative charge rod, while the negative charges are repelled away from the rod. This results in a positive charge near to the rod, an equal negative charge further away from the rod. Since the positive charge is near, la 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 la, the attractive force is greater than the repulsive force, la 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 la, net attractive force. Okay, look, here's what happens. عندك negatively charged plastic, عندك neutral. What's gonna happen؟ هون حيكون روحه كل البوزيتيف, right? Cause they're attracted to the negative side, صح? Makes sense. Since there's an attraction force between these two, but there's a repulsion force between these two, right? But what's closer? These two. So that means their force is going to be greater, so the attraction force will be greater than the repulsion force, hence they will attract. Okay? How many electrons should a neutral object gain or lose in order to acquire a charge of 7.4 times 10 to the negative? They should tell you that the elementary charge is equal to 1.6 times 10 to the power of negative 19 coulomb. They should be given. What is the formula for how many electrons? We know that the Q is equal to N times E. Q in this case is this. The number of electrons we're trying to find, and the elementary charge is 1.6 times 10 to the negative 19. It should be given. If you divide now 7.4 by this by this, you should get yeah, 4.625 times 10 to the power of 10. Okay, in a typical lightning bolt, you have a charge of 20 coulomb transferred from a cloud to Earth. How many electrons make up the lightning bolt? Again, they should tell you E, the elementary charge is 1.6 times 10 to the power of negative 19 coulomb. How many electrons? Same exact formula. Q equals N times, okay, N. Yeah, anyway, Q is equal to N times E. The final charge. Yeah. So sleepy. The final charge 20 is equal to the number of electrons times this, which is this. You put this in the calculator. I'm going to look at the solution. 1.25 times 10 to the power of 20. E should be given to you in the question. Okay, if it's not, just use this value. How is an object positive? What do you mean? Oh, okay. When an object gains electrons, becomes negative. When it loses electrons, becomes positive. Very, very easy. An old-fashioned gold leaf electroscope consists of two. This was a book question, by the way. Consists of two thin gold leaves suspending from a metal rod in a glass container. You electrify a plastic rod, okay, and then bring it near the knob of the electroscope. With the gold leaves separate. When you take the rod away, the leaves hang straight down once again. Use the model for electric charge to explain the behavior of the electroscope. Let's see. The negatively charged plastic rod will repel electrons from the metal cap to the gold leaves, causing the gold leaves to separate and rise, as the excess of electrons in the gold leaves leave them negatively charged. As the excess of, yeah. When we take the rod away, the electrons return and they hang straight. Okay, here I'm gonna draw on what sheet the gold leaf before I added the metal rod. It was like this gold leaf, they're repelled. Hello, when I add the metal rod, it's going to repel the negative charges and it's going to make them flow down. Negative, negative, negative. Down here. Until it flows to the gold leaves. Since the gold leaves are initially negative, they're going to repel more. You see, they're going to repel like this now. Okay, so it's going to repel the electrons to the gold leaves, causing the gold leaves to separate. La 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 la. But if I take it away, it's going to be back to normal and the gold leaves hang down again. Okay. 19. Explain how to distinguish experimentally between positive, negative, and electrically neutral bodies. Use always the gold leaf. Bring the body with the unknown charge near the cap of an electroscope, the gold leaf electroscope. If the leaves don't diverge, يعني أكيد the body is neutral. If the leaf diverges, then the body is charged. And you need to know the same, you need to know what the charge is. For this, you need to electrify the electroscope with a charge of unknown sign. يعني مثلا make it negative, make it positive. If after you charge the electroscope with a negative charge, for example, and you bring a charged body and it diverges more, يعني يعني the body that you got is the same as the charge was initially on the electroscope, which was negative, so that means that body is negative. If leaf diverges more, then the object is negatively charged. If it decreases, if the divergence decreases, that means it's opposite to the initial charge that you have on the electroscope, so it will be positive. Okay. What makes a person's hair stand when he or she touches the dome of Van de Graaff? Okay, the hair. Oh my god! Aha! The hair gets charged and repels like the leaves of an electroscope. Okay, that's pretty much it. إنه they're all gonna repel each other. يعني أنت شعرك هي هتصير positive positive or negative negative negative. No, it will be positive. Actually, Van de Graaff releases positive charge. So this is also gonna be positive 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 positive. كلهم positive. They're all gonna repel. هيكون كله ببعض. Okay. How does charging the spray gun help spray the paint evenly and helps save the paint? The solvent in the paint is a petroleum product. Okay, let's just read that. Oh my god. Okay, I'm gonna read this because it was mentioned in the book, but it's not in the quiz. So like maybe they get it if it's in the quiz revision. Paint drops are charged negatively as they leave the gun and are attracted to the wall. Okay, the wall which is grounded and it's positive. By grounding the surface to be painted, charged particles are attracted to the surface and depositing on it a thin coating. Static electricity can cause a sparkle that might ignite the petrol that's in the product. Forget the petrol, but yani, how does the spray gun work? And the cone positive wall, which was earth, right? How does it stick? Because احنا الgun تبعنا. Okay, الgun, this is a paint gun. YouTube, it's not an actual gun. Please don't get me demonetized. Uh, this is for educational purposes only. In case any, I'm just saying it in case someone reports me or whatever. Anyway, this gun, spray gun, paint gun, it has an electrode here that causes the paint to be released as negatively charged. And when it's negative, it's gonna form like some sort of coating on the positive to attract, right? That's pretty much how it works. In how does the lightning conductor help protect buildings? By the way, this question be very 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 important. Okay, please note. What happens what does the conductor do? The conductor provides a path for electrons to flow easily in huge numbers from the top to the ground. Thunderclouds carry charges, and if a negatively charged one passes overhead, it repels electrons from the spikes to the earth. The points on the spikes are left with a high positive charge density. The air between the cloud and the thick copper strip will be ionized, and the positive ions will be attracted to the cloud, leaving the negatively charged electrons to pass through the thick copper strip towards the metal plate. Okay, to sum this up, when lightning strikes, it always looks for the easiest path. And when you put all of these spikes وهيك, okay, it's basically giving the lightning. It's like, oh yo, it's like a way easier route if you like come by my side here. The lightning goes like, oh shit, okay, and then the lightning chooses to go through the lightning conductor because it's way easier for him to like move down. So what he does is he goes to the lightning conductor. It will put like a lot of charges here, which will repel charges down here, and this is usually goes underground. And when it goes underground, you guys know it becomes Earth, right? So that's pretty much wrapping everything up here. The air will be ionized. Okay, the air that's here will be ionized because there's a lot of like charging happening. So ما بتتحمل, like it doesn't like can't handle it, so it just gets ionized. How can static electricity help in seeing fingerprints? Okay, how do fingerprints work? And the specimen to investigate is on one plate connected to the negative, with a metal plate with powders connected to the positive. When sorry, the positively charged powder is repelled from the metal plate and hits the specimen, sticking only to the ridges of the fingerprint. So if you remember, in the drawing of the fingerprint, you had two plates with powder on the positively charged one. Since powder is on the positive one, it's gonna be repelled. It's gonna stick to your finger. Okay, well then it's powder, so it's gonna leave a mark, so you can see how the finger looks. Okay. Other powder particles lose a positive charge. Okay, so they repel back. So only the ones that stuck to your finger become positive, and they stay there, which shows you how the finger looks. How does the electrostatic precipitator work? Okay, a fine wire grid that's positive. It's put in the precipitator. Okay, so that a discharge will always occur between the fine grid and two concave metal. Okay, when smoke and dust particles are rise through the region, the charged dust particles are repelled from the wire grid and attracted to the earth plates where they are deposited. عندك الواير جريد هون، عندك البليتس هون. The dust comes here, it's repelled by the positive grid, it goes onto the plates, right? So that's pretty much it. Okay. هلا 21. On Jack's birthday, he has fun, okay, rubbing balloons on his jumper and then putting them against the wall. The balloons stick to the wall. Okay. If the balloons were given a negative charge, what type of charge did Jack's jumper get? Okay, guys, like, what's this shit? The stupid question. Okay, the jumper will be positive, right? Okay. Jack tried rubbing two balloons on his jumper and making it stick together. Would they? No, obviously not, because uh, they have like charges. Okay, yeah, يعني the balloons you both. شو هالسؤال السخيف يا أخي. You have two balloons. One when you rub them on your jumper بيصيروا negative. فأكيد if you put two of them beside each other they're not gonna stick together because they're both negative. In the expression F equals Q node E. My chair, oh my god. In the expression F equals QE, is the charge Q node the one creating the electric field or the one feeling the field? Okay, it's the one feeling the field. It was in the book. Okay, basically, here, this is the. I don't know why they wrote it like this, but this is the equation for electric field, and it's F over Q node. Okay, uh, this charge here, it's not to do with how much charge is like used to create the electricity. No, 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 بالعكس, that's the force. But the charge here, the Q, is actually to show how much charge is actually being under the influence of the field. So how much charge is feeling the field, as said in the question. So it's actually the one that's feeling the field. هلا 23. قربنا نخلص. You only have like 3 pages. It's barely been 15 minutes. What? Huh? 32 minutes? Oh, goddamn. Okay. والله I didn't even feel it والله. Define a uniform electric field. A uniform electric field is characterized by parallel lines and has the same magnitude and direction at any point in space. From the word uniform يا أخي, they have the same magnitude and direction. كلهم هيك. This is how it looks, by the way. Something like this. Okay. It looks something like this. They're all equally spaced. Yeah, mine isn't really equally spaced, but like you get what I'm trying to say. But they all have the same magnitude and direction. Describe electric field around the point charge. Okay, let's see. An electric field is a vector quantity. You must know that electric field is a vector quantity and it has both magnitude and direction. And honestly, I have a very huge feeling he's gonna get a question about the electric field in the multiple choice because Sarah he didn't put it in any of the AMSs. So I think he left it out on purpose in the AMSs. So we study it properly for the periodic. And he knows people won't study it, so he's gonna get a question from it. And I'm telling you how regional بيحب هيك. بيحب هيك. I won't say the words because يعني they're words I can't say on my channel. Anyway, an electric field is a vector quantity, and that means it has both magnitude and direction. The magnitude of the field at any point is the force per unit charge, right? The mathematical model that describes electric field is E is equal to F over Q naught, where E is the electric field, okay, F is the force, Q, okay, what the definition? You should know electric field is a vector quantity, meaning it has magnitude, direction. You should know that it's force per unit charge. Given E is equal to F over Q naught. Okay, very easy, guys. This is very simple. Draw the electric field around two positively charged particles placed near each other. That's it. Okay, they go away from each other because always it goes from positive to negative. There's no negative like place to go to. It just goes like away, like bam, bam, bam. You know what I mean? Okay. Memorize this, huh? Memorize it. يعني I'm not really, guys, and I'm not explaining a lot because, guys, I explained all these topics in the notes, so I explained them all in detail in the quiz videos. That's why ما إلي خلق to explain again. Now I'm just solving questions. But if you haven't seen the video for notes about electric field or you haven't seen the video about the quiz for electric field, make sure to watch it. What is the definition of SI unit of electric current? Electric current SI unit is ampere, right? Electric current can be defined as the flow of electric charge. What is its SI unit? The ampere, which represents the flow of 1 coulomb per second. Because, I is equal to Q divided by T. So it's 1 coulomb per 1 second. So the definition of it, it can be defined as the flow of electric charge, which 1 coulomb per 1 second. Draw a simple circuit and show the conventional direction of the electric current. Okay, this is any simple circuit, battery, and I don't know, put low resistor or lamp or anything. You put plus or you put minus. It's very important you put plus, you put minus. Okay, and then they ask you where's the direction of current. You just look at the arrow that's flowing from positive to negative. If I'm not wrong, yeah, I remember the physics AMS like it was yesterday. جابوا سؤال هيك شيء إنه which one shows the flow of current. It was like multiple choice. There was a few pictures you could choose from. But make sure you know it was multiple. It's gonna come multiple choice actually. A hair dryer draws 9.1 amperes. How much charge flows through it in 3.5? I equals Q over T. Charge would be equal to IT. Current is 9.1. Time is 3.5 minutes. 3.5 minutes. You want to convert it to seconds? It's gonna be times 3.5 times 60 because each minute is 60, right? And you get, let's see, 1.9 times 10 to the power 3 coulomb. 2 coulombs of electrons have left the negative terminal of a 1.5 volt dry cell to the positive terminal through a thin wire. How much heat energy is released in the wire? Where does this energy come from? Energy, W equals Q V. W equals the charge 2 times the volt 1.5, which is 3.0. Where does energy come from? I honestly don't know. Where does it come from? It comes from the electric potential energy in the dry cell. Oh, okay. Anytime you have a circuit or you have any conversion of energy, that means you had electric potential energy. Potential energy means it has the potential to be converted to a different form of energy. أكيد it started off as electric inside the cell صح؟ uh, وبعدين became heat energy, so يعني there was some potential energy. Uh, what is the energy released by a 5 coulomb charge with potential difference 3? Same as question 29, W equals QV, 5 times 3, 15. For each of the following, indicate the type of energy that's being converted to electric energy. Battery, أكيد chemical. I'll just show you. Chemical potential. Thermocouple, anytime you see any thermometer, you think temperature. So heat energy, right? Heat energy. Electric generator, it moves and goes like, it's like, it just keeps on moving, which causes mechanical energy to be converted into electric energy. Okay, photoelectric cell, it's like solar panel, it uses light energy. Okay, what is the current drawn by a 2 kilowatt electric heater connected to a 220 volt supply? Current, okay, you have power and you have voltage. They want the current I. You know that P equals IV. So I equals P over V. So 2 kilowatts, and it's 2000 watts divided by the voltage 220. Okay, you're gonna get 9.09 ampere. Okay, if on average the heater operates, let's put 9.0, 8 hours a day, what's the total energy consumed by the heater in one day? Energy is equal, or work is equal to power times the time, right? Any two equations. You can use W instead of E, doesn't matter. The power is 2 kilowatts, which is 2000 watts. But the time is 8,000 hours, 8 hours a day. And what's, do I put as 8? No, definitely not. We need to put it in seconds. How do you convert from hours to seconds? You multiply by 3,600. Let's see. 2,000 times 8 times 3, 600. Oh, they want in mega probably. On scientific notation, 5.76 times 10 to the power 7. Is that correct? 1, 2, 3, 4, 5, 6, 7. Yes, correct. Okay, a battery of EMF 4.5 volts is used to operate a bulb. Oh, ما بدنا يخلصوا. عمى. 1, 2, 3. Okay, they get easier. Okay, here بصراحة it's like one more long question. It's like they're annoying, bro. They're annoying because until you see the question, it's like a paragraph. ما لك خلق. A battery of EMF 4.5 volts is used to operate. The bulb draws a current of 0.8 ampere. but the potential difference is 4.1 volts. Calculate the energy that 1 coulomb of charge gains in the battery. Huh? In the battery. I think it's just W equals roughly charge. Hold on. Charge is 1 coulomb. A Q1 times 4.5, صح? Yeah, okay. Okay. Yeah. So the energy that is inside the battery is equal to the EMF for 1 coulomb, right? Well, the EMF in this case is 4.5. Anytime you're still inside the battery, 4.5. What energy is lost by 1 coulomb in the battery? How much? 4.5 minus 4.1, 0.4 joules, huh? Uh, when energy is lost by 1 coulomb in the battery, 0.4 joule. Yeah, okay, 0.4. Okay, yeah, makes sense. Since we're saying 1 coulomb, W equals QV, and when Q is 1, yeah, you can just not include it, okay? Okay, find the energy that 1 coulomb of charge delivers to the bulb and wires. W equals QV. The stuff that's actually being delivered is 4.1 volts. We're saying 1 coulomb, so Q is 1. So it's 4.1 joules being delivered. Is this correct? Yes. Uh, a car battery is rated 70 ampere hour. So I think this is IT. What is the amount of charge traversing a circuit branch to the car battery? I think it's just 70. Wait. Yeah. This is time in hours. Okay, yes. Amount of charge is Q equals IT. In this case, the current is 70, with the time is 1 hour. And 1 hour has to be in seconds. So 1 times 3,600. Or you're gonna get how much? This number, 252,000. Define the EMF of an electric generator. This is very important because it comes in the exam. The EMF is the energy supplied by a generator to transport 1 coulomb of positive charge from the negative terminal to the positive terminal. That is what we call electric force. Okay. Using the minimum number of elements, set up a circuit to test the conductivity of objects. Use standard notation, draw a suitable diagram. We want to use the minimum number of objects. Should we don't test the conductivity of an object? Use a standard notation. Okay. Consider silver wire, a Constantine wire, and a plastic ruler. Connect each of the above wires separately in series to a circuit containing a 1.5 volt cell and an ammeter. Okay, you will notice that the current is maximum when the silver wire is connected. Current will decrease through the constant wire and no current will pass when the plastic ruler is connected. Therefore, silver is a better conductor than constant, while plastic is an insulator. So we want to see conductivity, and if it does conduct electricity, does it not? So you're gonna want to test different materials, right? Silver wire, constant wire, plastic ruler. Okay, and then you have the ammeter, so it's gonna show you if current is flowing or no, right? So whenever you use مثلا the silver wire, it's gonna work the best. You're gonna get the best current. It's constant and wire, you're gonna get less, and then when you use plastic ruler somewhere here, it won't work at all. Okay, using the minimum number of electrons, set up a complete circuit containing as the minimum number of elements. 3 lamps in series. Okay, we're just gonna look at the answer here. Okay, then you want you to draw it. 3 lamps in series. Just draw a circuit. 1, 2, 3. Easy. 3 lamps in parallel. Again, very easy. 1, 1, 2, 3. Right? 2 lamps in series while with the combination in parallel with a third lamp. So in series, and then it's parallel with a third lamp. That's pretty much it. Draw the circuit symbols for each of the device below. Variable resistor, it should just be like this. Potentiometer should be like this. You switch it like this, left and right, even though it's not required. Heater is like this. Well, this is the thermistor, right? Thermistor. Okay, 39. Draw a series circuit consisting of 2 resistors and a cell. Take the characteristics of the resistor. Observe. This is series, has 2 resistors, has a cell. The current in the resistors are the same, but the voltage of the cell is divided across each resistor. Remember that the voltage in series circuits are added. Okay, taking electric measurements. How is an ammeter connected? How is a voltmeter connected? An ammeter should always be included in series. Okay, and the polarity must be respected. It's very important that the polarity must be respected. A voltmeter measures the potential difference and its terminals must be connected in parallel, right? هنا قربنا نخلص. What is the value of current X? This came copy paste in the exam. It was 3 ampere. 2 plus 4 is 6. 6 minus 3 is 3. Haram if you got that wrong, wallah. I know some people that was their only mistake. You know what? How? In the circuit below, the voltage across the battery is 24. Resistors 2 and 3 are identical, and the voltage across resistor 1 is 4 times resistor 2. Using Kirchhoff's voltage rule, determine the voltage across each resistor. Okay, let's write it like this. R2 is equal to R3. Okay, and they said that R1 is 4R2. Right, so R1 is 4 R2. We know that R1 plus R2 plus R3 equal to the total voltage 200 should 24, right? Let's see. Let's start substituting. R2 is equal to R3. So instead of R3, هنحط R2. So R2 plus R2. Instead of R1, we're going to put what? 4R2 because they said R1 is 4 times R2. So 4R2 equals 24. You're going to get R is equal to 6. Let me see. Yeah, so R is equal to 6. Sorry, R2 is equal to 6. And they want each resistor. If R2 is equal to 6, R1 is 4 times R2. So 6 R2 is 24. Should be, no, it should be R2 is equal to 4, not 6. Okay, if R2 is equal to 4 ampere, then R2 is equal to R3. So this is 4, 2 ampere as the ohm. Oh, R1 is 4 times R2. So just 4 times 4, which is 16. Very easy. Okay, they did it like me. It's okay. Okay, calculate the EMF of the group if the EMF for each cell is 2 volts. Okay, it's very easy. Here, akid is I'm gonna open the solution. The first one is gonna be 0. Why? Because they're opposite to each other. It's not grouped properly. It should be negative, positive, negative, positive. But they put the positive with the positive, so it's gonna cancel out. It's gonna be 1.5 SI. 2 minus 2, 0. Here, they're placed properly. Positive, negative, positive, negative, positive, negative, positive, negative. Opposite to each other, which is the correct way. That means it's gonna add up. So 2 plus 2 plus 2 plus 2 is 8. Here, they're in parallel. In parallel, no matter how many you add, it's always going to be the same. And that is the original EMF, which is 2. The potential difference across the terminals of a dry cell is measured when current is drawn. The potential difference is 5.5 when the current is 1, and 5 when the current is 2. Determine the internal resistance and the potential. Oh, okay. This is nice. Of the cell and the potential difference across its terminals when no current is drawn. Okay. So here for this one, what they're asking is the internal resistance. Resistance yani how much was lost, right? So you're gonna use whenever you're using, R is equal to V over I. But whenever you're using the equation where you're seeing that some voltage was lost, you're gonna use R equals E minus V over I. You use this, and I mentioned it in my notes video. Make sure you go back and watch it. Okay, let's see. We know, they want us to determine the internal resistance across the PD. Okay, when no current is drawn. Okay, when no current is drawn from. Okay, now what do we have? We have the voltage and we have the current, right? So let's like let's rewrite this equation, right? Let's write it in terms of let's write it in terms of we don't have the resistance, we have current, we have. Yeah, and I don't know why this is taking too long, and I'm pausing the recording. I'm just looking at the question. But it's obvious what you have to do. You just substitute E minus V at the start. We don't know what E is. We know that the voltage is 5.5 over 1 is equal to R. This is this first one, right? Okay, I'll redistribute this. You're going to get E minus 5.5 equals R. Now we're trying to find the potential difference when there's no current. When there's potential difference when there's no current, they're basically telling you what's the EMF. When there's no current, the potential difference is equal to EMF. Remember, E is equal to V when when I equals 0. Okay, so you're gonna get that the E, we're trying to find it. E, it's 5.5 plus R. That's the first one. How about if E1? Okay, how about if we substitute E2? Let's use the equation Ri plus V, right? Or you know what? Actually, no. Let's substitute the same way I substituted the last time, just so you guys don't get confused. Again, R will be equal to E minus the voltage in the second time, which is 5 over 2. Cross multiply, you're going to get 2R, and then take equals E minus 5. Take it to the other side, you're going to get 2R plus 5 equals E. So E2. Now we know it's the same battery, it's the same circuit, right? So isn't E equal to E? Yes. So 2R plus 5 is equal to 5.5 plus R. And if I'm not wrong, you're gonna get, I think, 2. Wait, this goes there, this goes there. You're gonna get R. You get R equals 0.5. So we found the resistance. Can we find the potential difference now? We just substitute 0.5 into any one of these. This is easier here. You can get E1 is equal to 5, uh, I don't know, volts, right? Uh, you're gonna get, true? How do I get, how am I, oh my god. Yeah, kid, if it's 5.5 plus R, we know R is 0.5. It's gonna be 5.5 plus 0.5 is 6. I'm so tired, so drunk. مش مركز. I'm not focused on it. You know what I'm saying? What are the factors upon which the resistance depends? What is the relation between resistance and resistivity reduced to SI units? Let's open. What does resistance depend on? The resistivity, length, and cross-sectional area of the conductor, right? Such that R is equal to the resistivity times L over A. The unit of the resistivity is ohm meter. Okay. So what does resistance depend on? Remember, R is equal to rho L over A. So it depends on these three things: the resistivity, the length, and the cross-sectional area. Okay. Uh, what is resistance? Resistance is the amount of energy as the ratio of potential difference to the current. Remember, R is equal to V over I. Always start with the formula. Potential difference to current, to its characteristics, its property. It is a characteristic property of conductor called resistance, usually noted by. Okay, just say resistance is the value of the current potential difference divided by the current. Okay, the voltage is 50 across the. Okay, this was in the quiz. Okay, what is the current? They gave you a resistance. They gave you V. They want I. R is equal to V over I. Switch is going to be I is equal to V over R. 12 divided by 50, and you're going to get 0.24. Last question for today. A spool of 20 gauge copper wire at 20 degrees Celsius has resistance of this. Calculate the length of the wire knowing that the cross-sectional area is this. Given the resistivity. Okay, this is a nice question. You know what? Actually, I won't take it. Well, let me just solve it. Okay. Now we don't care about the temperature. They give us R. They want the length L. They gave us the area is this. They gave us resistivity is this. Okay. Here's the thing. We know the equations R is equal to resistivity L over A. Very self-explanatory, but it's very important that you pay attention to the unit of resistivity if they give it to you in centimeters. Here's how you do it. I want you to convert it to meters. But what's different here is that you can't just do times 10 to the power of negative 2. No. Here's the thing. The resistivity's unit is 1.72 times 10 to the power of negative 6 ohm per centimeter. So if you want to convert it to meters, you don't just multiply by 10 to the power of negative 2. No. You multiply by 10 to the negative, you multiply by 10 to the power of negative 2, but it has to be in the denominator. Why? Because centimeter is in the denominator in the unit. Okay? It has to be in the denominator. So let's solve. Okay? R 0.655 equal to the row 1.72 times 10 to the minus 6 over 10 to the minus 2. Okay, this is your row, and then the length, and we're trying to find it, over the area, which is millimeter squared. To go from millimeter squared to meter squared, what do? You do times 10 to the minus 3 squared, right? So times 10 to the minus 6. So L over 0.517 times 10 to the minus 6. Okay, let's do this on a calculator. 0.655 equal to, لا مش equal to 1.7, no, is equal to 1.72 times 10 to the minus 6 over 10 to the minus 2. Hold up, shift صح. شو ليش؟ صح, I didn't put, I forgot about, I'm so sleepy. Times the length x, I just keep it x, over, down we have 0.517 times 10 to the minus 6. 0.517 times 10 to the minus. It's a shift. So you get this. I don't know why I feel like this is wrong. Uh, okay, we got it correct, but we did something wrong. Let's go again. Okay, let's use the equation. We know it's R is equal to rho L over A. Let's rearrange it. We're looking for L. Multiply by A, you can get RA plus RA over rho is equal to L. Okay, نحنا our resistance is 0.655. Area is this. We're gonna multiply by 0.517 times 10 to the minus 6. Right? We're gonna keep it like that because why? We said from millimeter squared to meter squared, you have to do times 10 to the minus 6. 0.517 meter, sorry, times 10 to the minus over the rho. In this case, the rho is this. And like I told you, I'm convinced that you need to make it like, I don't know, what did they use in it? This is wrong. Should be wrong. Oh my god. Oh my god. I just realized that the unit of resistivity is ohm times meter, not ohm divided by meter. Okay, yeah, then, yeah, okay, shit, that makes way more sense. If you want to convert, okay, yeah, that makes way, way more sense. But other things are not always like this. Okay, 1.72 times 10 to minus 6 ohm centimeter, right? You want to change this to meter. It's 1.72 times 10 to the minus 6 times 10 to the minus 2 to make it meter because it's in centimeter. I thought you had to do something. I thought it was over here. Anyway, you're going to get 1.72 times 10 to the minus 8 down. Is that correct? Yes. So we should get the correct answer here. 0.55 times 0.5, sorry, 0.517 times 10 to the power of minus 6, and then down 1.72 times 10 to the power of 8. Okay, okay. Negative 8. Negative 8, right? Because minus 6 minus 2 comes minus 8. Now should be correct. 19.6, which is rounded 19.68, which is rounded to 19.7. هيك خلصنا. Thank you so much for watching. Good luck in your periodic.